Space exploration has become a great field of study by students ranging from elementary school to major universities. Most major universities have launched some type of picosatellite to perform tasks such as capture images, measure temperature, or magnetic fields. USF has fallen short from this list, and we are seeking to join the list of universities with satellites in orbit. To solve this problem, we decided to engineer the electrical power unit so that future design classes could build off our initial design to ultimately have a USF launch. A picosatellite is comprised of multiple subsystems, the most important one being the power systems or EPU that will power every other component in the picosatellite.
Ideally, the EPU consists of solar panels, charging regulator, main controller, and voltage regulators, more commonly known as LDOs. With these components, we plan to have full control of the charging cycle, output regulator triggering, and protection circuitry. The microcontroller of the EPU will monitor the status of the battery voltage. If the batteries are not charged, the controller will notify the main CPU of the battery status, where the main CPU can then decide to activate the charging circuit. If the charging circuit is activated, the controller goes into power saving mode and shuts down the LDOs. During this time, the controller will monitor battery voltage and give status updates to the main controller until the batteries are sufficiently charged. Once the batteries are sufficiently charged, the main controller could then decide which function it wants to operate.
Of our multiple requirements, our top three are two separate power modes that will be controlled by the main CPU, power circuitry, and flexible interface for future subsystems. To meet these requirements, our design was built around the ATmega 328P as the EPU's main controller, which monitors the whole system and works as the foundation of our protection circuitry. This chip is accessible via its I2C bus, where status updates can be sent and commands can be given. The charging circuitry is controlled by the LT3652 solar-powered charger, which is a switching buck converter. Shown here is the chip's capability to automatically adjust the output pulse width when the solar cell input voltage changes due to the built-in voltage feedback.
Our final structure design provides the necessary interface for future design teams to fit their boards. Header pins were fitted for seamless power and data connections between multiple circuit board layers, and commonly grounded mounting rails allow each board to be mounted securely. Connecting to the I2C bus through the header pins, we were able to test the functionality of switching on and off each device. Here, a command is sent to power on each 5V and 3V voltage regulators. After some time of loaded operation, battery voltage status is then requested. A value is received that is then verified with a multimeter. Here is a demonstration of our charging circuit operating outside at 100 milliamps. And here it is connected inside for an extended period of time. To test the protection circuitry, we short-circuited the output and tested the microcontroller's response. Channel 2 in blue represents a voltage or current spike, while channel 1 in yellow represents the response of the controller. In these preliminary tests, the propagation delay was higher than the time set by our requirements. To mitigate this, we used the built-in interrupt in the microcontroller as well as port manipulation. In this image, the response time is lowered to 1 microsecond, which meets our initial requirement.